Welcome back to the lecture series on image recognition with neural networks. This is lecture 3, Formalizing the Problem. Our objectives are to understand what a loss is over one training example. We'll talk about the cost and the objective function, vectorization and broadcasting. And then we'll talk generally about the training process. Recall that in the first lecture we talked about the MNIST dataset where every image is a tuple, xy, where x is a flattened column vector of pixel values, and y is the corresponding one-hot vector encoding of that image. And we want a classifier or a function that maps the raw pixel values to the label space. And what we want is that we want the prediction f of x to be approximately the same as the label vector y. And we talked about how this is going to be an n-layer neural network that depends on these parameters wi and bi, the learnable parameters of the network. And so we want to make precise the statement that two vectors are approximately the same. And to do this, we're going to define the distance between vectors. So again, the y vector is the one-hot encoding of the image, whereas the f of x is the vector of prediction of the same image x. And so we want these two to be similar. In other words, we want f to model the training set. So given two vectors, u and v, which is vectors in Rn, the distance between them is defined using the Pythagorean theorem, the generalized version of the Pythagorean theorem. In other words, again, the notation here is that you definitely have seen this in precalculus when we talk about vectors. We subtract the two vectors, and then to find the magnitude of that difference, we simply subtract all the components of u and v, square them, and then sum them up, and then take the square root. So again, this is just the distance formula for two vectors in Rn. And then the shorthand notation for this using summation is here. And to make the algebra simpler, in fact, we're going to be using the square distance, and the square distance is simply we square this expression, and so there's no square root. And so we're going to define the square distance between two vectors as the sum of the squares. And this will be a little bit easier when we do some of the calculus later. So for example, if I have two vectors u and v, the distance between them is, well, let's subtract the components. So 2 minus 5 square, 4 minus 0 square, and then 1 minus 1 is also square. We sum them up and take the square root, and this is 5. So the distance between these two vectors is 5. And the square distance is 25. Again, the square distance is simply ignore the square root. So we need a training set so that our computer can learn from data. So suppose that we have m label images. Again, label images means that we have the pixel value, which is given by x superscript 1, x superscript 2, etc. So those are the pixel value, and then the y superscript 1, etc. will be the label that corresponds to that image. So we need to have the pixel value and its label so that computers can learn from those data. And again, the x vectors in R784 and the y are vectors in R10. So we're going to call a superscript I to be the output of the ith training example. So again, x superscript I is the image in the training example, and when we apply our model or function to it, a superscript I is the prediction vector. So what we want again is that a superscript I to be approximately the same as y superscript I, the prediction to be approximately the same as the label. And so for each of our training example, we want to measure how well our model performs in predicting that one label. And so we call this the loss of that training example, or the error of that one training example, and we denote that by L of AI, YI. And so again, here's the prediction, and here's the actual label. So the loss is the measure of the error between our prediction and the ground truth, the true label. So that's the loss of one example. So there's a lot of ways to define this loss. We're going to do something very simple, and we're just going to take the square distance between the two vectors and then divide by 2. So again, this measure approximately the distance between the prediction and the label, and the square to make things a little bit simpler with the algebra, and the 1/2 we see later will also make the calculus a little bit easier. I mean, this is just a constant, the 1/2. We don't really need it, but it will make things a little bit easier. So again, this is a measure of the error or the loss of one training example, how well our model performs on that one training example, the ith example. We now define the cos, or the objective function, to be the average of all the losses over all the training examples. And this function basically measures how well the model performs over the entire training set. So again, this is the loss or the error of one training example. We sum up the errors over all the training example, divide by m to take the average. So this is the average error or the average cost of this model. And notice that the average, this cost depends on w and b. In other words, if I change my w and my b, my parameters, then I might get better or worse models. And so we want to find the parameters w and b. And these are the learnable parameters wi and the bi. We want to find the best parameters so that this cost function is as small as possible. Because if the error is small, then that means that our model is doing a good job at recognizing those images. So this is a very important function. Sometimes this function is also known as the mean square error in statistics. So here's the error again. Again, this cost function depends on the parameters of the network. So we want to find the parameters that minimize the cost, therefore maximizing the accuracy of the model f of x, again, which depends on those parameters. And once we complete the training process and found the optimal parameters for our network, we can just throw away the training example, the training sets, and we can use these parameters to make predictions on new images. In fact, we saw that in the first lecture notebook where I loaded the optimized parameters that's been previously trained, and we use those optimized parameters to make prediction, just as an example. So let's do an example. So suppose we have a model, a simple model that maps from R2 to R2, and say we have 3 examples, x1, x2, x3, and then the corresponding label. So let's just say that the label y1 is 0, 1, y2 is 1, 0, y3 is also 0, 1. These are the one-hot encoding label. Suppose that our function predicts the prediction for the first example is 1, 2. The prediction for the second example, A2, is 2, 3. The prediction for the third example is the vector A3, which is 0, 1. And notice these predictions are not perfect. This one has an error, right? It's not exactly the same. This one also has an error there somewhere. And this also has, oh, actually this one over here is actually exact. Okay, now we compute the losses and the total cost. Again, the loss between the prediction vector and the true label is simply the square distance between the two vectors divided by 2. So if I subtract these two vectors a1 and y1, I get 1, 1, and I use the magnitude, find the magnitude of this vector, and then I square that. So it's 1 square plus 1 square. This is the Pythagorean theorem. Then I divide by 2. So that error is 1. In the same way, the loss over the second prediction and the second label is, again, find the square distance. The difference here is 1, 3. So Pythagorean theorem is 1 square plus 3 square. Divided by 2 is 5. And then the loss of the third example, we don't have to even do it because these are exact. So the label matched up exactly with the prediction. So the loss there is 0 because there's no error in that prediction. So these are the 3 losses over the 3 training examples. So now to compute the total cost of this model over all the training examples, we add up all the losses, all the 3 losses, divide by 3 to take the average of all the losses. So in this case, the average cost or the objective function is 2, which is the average of all these three losses. So what we want is we want this cost function to be as small as possible because we want our function to be as accurate as possible. Again, this is a measure of error of our model. So the losses are the individual errors, and the cost is the average error. Vectorization. So remember that from the previous lecture, we talked about an n-layer neural network where we have an X image, and we send it forward by applying the affine function to it, multiply by the W1 plus B1, apply sigmoid to it. We keep doing this n times, and the last output is the prediction vector. So if we were to do this with our training set, we have to apply the network to one image, then apply it to another image, and keep applying this whole network to individual images. And so we need to do some kind of a loop to feed forward these images and get prediction f of x, and then loop through all the training examples. So it turns out that in Python, looping is a slow process. We want to be able to use NumPy's optimized matrix operation to feed all of the training set without using any loops. So this is called vectorization. It's the idea of making prediction on all the images without using any loops. And we take advantage of the NumPy linear algebra library. And so the way we do this is that instead of sending over one image x, we take all the images and put it into one big matrix, big X, and send forward to the network. So this is now a big matrix of whose columns are all the images, and this is a big matrix multiplication. Again, because now we don't have to do any loops, and this operation in NumPy is very fast, the matrix operation for multiplication. And then we go through this and notice that instead of doing this for all the images, we take this X and we send it over forward to the network only once, so that the output of this is a matrix of predictions for all the training examples. So this is vectorization. I noticed we'll talk about this later, but there's an issue here that we call that can be solved by broadcasting. And again, we'll see an example a little bit later, but the idea here is that because we have a big matrix X now, this product will give you a matrix that is not compatible with this column vector. So this is a column vector, and this is a big matrix, so we can't add it because this is not compatible. But NumPy's broadcasting will allow us to add this in the way that we want, namely add B1 to all of the columns of this product. Okay, so to prepare for vectorization, so let's say we have this training set of M images that are labeled. We take out all the images, all the x's, x1 to xm, and we horizontally form the columns of big X. So this is one image column of 784 by 1. This is another image, etc. So these are the M images. So we have a big matrix of all the images, all the picture values of all these images. And so this should have dimension for us 784 rows, because that's the dimension of each image. And then M is the number of columns, because M is the number of images in the training set. We do the same thing for the labels. We take all the labels Y, and we stack them horizontally, forming columns of this Y matrix. So each column is 10 by 1, so therefore this is 10 by M matrix. So in NumPy, there's a function called hstack that allows us to do this. So let's see how this is done in Jupyter Notebook. So as before, we load the data set, load NumPy. So here's vectorization. So again, we have M label images, and we want to stack them horizontally. So if you have a list, a Python list of 2D NumPy arrays, M by 1 2D NumPy arrays, then the function hstack, send over the list, will produce a NumPy array M by N. So again, X is the list of arrays, whereas but the result of hstack is a NumPy array. So we want NumPy array to do matrices and their operations with the NumPy library. So here we input the NumPy library, and let's just do a simple example. X1, we're going to create a small 2D array. So we want this to be 3 rows. So here's the first row. Let's actually do 1, 2, 3. So 3 rows in one column. We do the same thing for the second matrix here. So this is another column vector, say 4, 5, 6. So this is printed out. Make sure we see what it looks like. So here's this one. So here's again a column vector 1, 2, 3. Okay, now what we want to do is we want to stack them horizontally. So let's do that. So I want to first of all make a list. So this is a Numpy list using brackets x1, x2. So again, this is not a 2D array. This is just a list of those vectors. We can do matrices operation on this list. And then now we're gonna save it into x again, but now we're gonna stack it horizontally. A stack on x. So run that. So if I were to print out x, and notice we have now, this is a 2D Numpy array where the xi stack horizontally. Okay, let's write a function vectorize mini batch. This function will be used in the last lecture where we put everything together into one big program. So this is a very important function. So it's supposed to have a mini batch of image label tuples, as we saw in the lecture, and we want to use a stack to form xy, where x is again the set of all pixel values for all the images, and y is the big matrix of all the labels for all the images. And so let's write this. Okay, so we're gonna so here's a mini batch of again a list of image label tuples, and we're gonna first create 2 lists of images and labels, and then we'll stack them. Okay, so again, this is just a Numpy list. So we'll do a for loop, I in this range from 0 to the length of the mini batch. Again, we'll talk about why this is a mini batch later. For now, say this could be the entire training set that we want. So this could be 50,000 images, and we're going to just stack it horizontally to vectorize. Okay, so for each I in this range, we're going to take our mini batch, so mini batch x, and we're going to just append to it. We're going to add to this list. So this is we want this to be the images. So mini batch, again, bracket I gives you the ith image, image tuple, and we need to extract the image pixel. So we need to extract the first component, which is 0. And then we do the same thing for the mini batch y. So mini batch y, we're going to now take out the labels, which is the second component, which is at index 1. Again, we saw this in the first lecture. So this will give us a list of image pixel values and a list of label values. Okay, and then now we're going to stack it. So x is going to be now np.stack mini batch x. So this will take the list and then stack it horizontally. So this is actually a stack. And then we're going to do the same thing for y. This is the stacking all the labels. So this is y. And then we'll return the tuple x comma y. So there it is. Let's try it out. Okay, so suppose I want to, this is called, in fact I have here this state line. So let's here I'm calling the function vectorize mini batch, and I send over the first 20 images of the training data, and then we want to return the xy tuple, where again x is the images, y is the label. So let's run that, and now we want to print out, for example, just the shape of it. Same thing for y, and we want to make sure that this is the right shape, and it is. And notice that this is all the images 784, because there's 20 images, then the number of columns is 20, and each image is a 7084 vector, so this is 7084 by 20. The label is 10 by 20, so that works. Okay, let's go back to this. In fact, we can actually use this now to kind of see what. So why do we want to do this? Well, again, so here's the sigmoid function again that we saw from the first lecture. This is the it's part of our neural network. So we wrote this in the first lecture, so we use this again. So again, this is why we're doing this. Here's the x again, all the images. Now we can use the entire training set x, and we can just feed forward into the network only once. Again, this is avoiding for loops. So if I apply my model to the entire x, I'm basically applying the model to each of the individual images. We want to do this only once without having to do for loops. So let's kind of see how this is done with the function. In the first lecture, we wrote this function where x was only one image, but now x is a matrix of images. And so notice the code here is actually exactly the same as in the first lecture. We take w1, which is our parameter, and we multiply it by x. And then again, this is a big matrix, and then we add b1. So we saw in the lecture that, again, there's some issue here with compatibility. Right? This is a big matrix after we matrix multiply. This is one column, so this is not compatible, but Numpy will broadcast it automatically for us. And so again, in a second, we'll do an example of that. And then we apply sigmoid to this. Again, this is now a big matrix, Z1. And we do this again for A1, and then so this output is a matrix of predictions. In other words, it has the prediction for all the images in the training set. In the first lecture, we only have the prediction for one image. Okay, I want to clarify this broadcasting. So in lecture 2, the previous lecture, we talked about broadcasting. So I want to kind of give you an example. Yeah. So again, we are vectorizing. So if we don't vectorize and we use only one image x, let's say one column vector, then there's no issues because we multiply this, and then this is one column. We add it to the b column vector, and then we get an answer. So there's no issue there. But when we vectorize, we have to form a big X, which is all the images. So for example, if I have two images, two columns, then when we do this matrix multiplication, then this is a bigger matrix now. We'll have two columns, and it won't be compatible with this one column. So you can't add a vector to a matrix because again, this will be the same as the number of columns, the number of images in the training set, and this is we'll only have one column, whereas this will have m columns. And so Numpy would do something called broadcasting, where it will take this one vector and just stretch it out horizontally, so that this one vector can be added to all of the columns, and that's exactly what we want if we look at the algebra. And so this is done automatically. We don't have to worry about it. So that's why in this code here, even though this is a big matrix and this is one column vector, broadcasting allows us to just stretch this out so that we can add this one column vector to all the columns of this product. Okay, great. Okay, let's just kind of see how this is also going to help us when we make predictions. So for example, we wrote a version of this in lecture 1. So now let's write the vectorized version of this, where we want to make prediction on a bunch of images and not just one. So we're gonna let's see. Okay, so we're gonna vectorize this first. So let's I'm gonna call vectorize mini batch on the images. So again, this is the function we wrote previously, and it will return to us the xy tuple. So, okay, now we can make our prediction. I'm going to call f, which is the function we just wrote up here, which is it's going to take all the images of our training set. So we're going to call it on x, and then we'll send over w1, w2, v1, v2. So that's the prediction of all the images. And then we're gonna say the prediction. Okay, so this is a little bit tricky, but so again, this is the prediction of all the images. That means that every column is a 10-dimensional class scores, and the biggest class score, the index of the biggest class score, is the digit that we want to predict. And so the way we do this is we're going to use np.argmax. But whereas previously this is done to only one vector, now we have to do the entire matrix of prediction. So we're going to do np.argmax on A, but we need to use an axis. Again, this is in the previous lecture when we talked about taking the axis of something. So we want this to be axis 0 because that means we're collapsing all the rows, meaning that we look at each column and we find the index of the biggest class score and return that index. So this will give us the prediction for all the images all at once. So again, please look over that lecture too if you're not sure about how this is done, but this is important to understand. And so this is now a Numpy array, and so this is actually, we want to return a list, so we're going to convert this into a list. Okay, and then we return this predictions. Okay, let's see how this can be done with a bunch of images. Let's load the parameters again. Again, this has been trained already. These are the trained parameters, which we'll talk about later. And let's call predict on, say, the first 20 images. The training set, training data. And we need to send over all the parameters that we just loaded, W1, W2, V1, V2. Notice that now it just predict for us the first 20 images. Okay, great. So let's go back to this. Okay, so I'm going to finish by talking about the training process in general and kind of see where we're going after this lecture. So here's what we've done so far. To train our neural network, we start out with all the images and labels, and we're going to form X and Y, vectorize it. And so here's our training set X, here's our label Y. Then we're going to randomize our parameters. Again, we want to find the best possible parameters to model our images. And so initially we don't know what they are, so we're going to just randomize it. And after having randomized it, we have now a function, not a good one because these are randomized numbers, but we do have a model for our for F. And so we're going to use those parameters and just feed forward all the images X into the network. So this is all the affine function, the sigmoid, the composition, the n-layer neural network. So f of x represents the output of prediction. There's a big matrix of prediction that we just saw in code earlier. And so now we want to look at the prediction f of x, the matrix of prediction, and see how it relates to the labels. We want to kind of measure the error between the prediction and the label or the loss. In fact, when we look at the average of all the losses, we call that the cost function or the objective function, and we denote that with the function j. And so this is the total cost over all of the training set. So again, initially this is a bad function because it's a high cost because our model is a randomized model. All parameters are random numbers. So what we want to do next is that we're going to look at these parameters and say, can we do better? And so the next step is an algorithm called gradient descent, and this is an algorithm that will tweak these parameters W and B so that the parameter better reflect the data. And so when we tweak the W and B slightly, the effect of that is we want to reduce the cost. In other words, we want the error to go down. And so gradient descent is an algorithm that allows us to do this. And so we take gradient descent is a loop. So every step we make a slight change to the parameters. And so now that we've applied one step of that, we have new parameters, and we do this over again. So we use those new parameters, which is slightly better than the old one, send forward all the images, and then calculate the cost again, and then apply gradient descent again to tweak the parameter slightly. And we keep repeating this process. And at every step, we slightly change the parameter to better reflect the data. And as we loop through all these steps, then we want the cost to go down to 0. And by the time when it does get down to 0, then we found a good set of parameters that can classify images. And so this is kind of the big picture of where we're going in the next couple of lectures. So really all we need to understand next is this algorithm, which is the main algorithm of the entire program, which is gradient descent. And so a couple of things I want to say before we end is, so at every step of gradient descent, notice our model, our function, is a function of x, and these are the parameters. And so these are constants at any given step. These have been fixed. On the other hand, the objective function, the cost function, is a function of the parameters. So now the data is fixed, so that this is a function of the parameters only. And so this distinction is very important, that f is a function of the images, x, and j, the cost function, is a function of the parameters, w and b. So all we have left is to understand the gradient descent algorithm, and then we can finally write our entire program. However, this algorithm does require some calculus, which we'll discuss just intuitively in the next lecture. So again, this video has a homework assignment on Jupyter Notebook, and so please see the links below for the description, including the code that we wrote in the video. Okay, I hope to see you in the next lecture.